Alright, so I want to discuss the limit definition of the derivative here for a few minutes, and I want to use it to evaluate a simple polynomial, f of x equals x squared. This function is often referred to as just the algebraic parent function because its graph is so familiar to all of us in that it just looks like this, right? It's a very easy function to work with. It's an extremely useful function, and if you continue watching these videos on this derivatives or differentiation playlist for my Cal 1 set of videos, then you'll see that x squared prime, or the derivative of x squared, is going to be something that's not only extremely easy to arrive at, but also that's very useful as we continue our journey through the world of calculus and analytical geometry. So, all right, let's recall really quickly the limit definition of the derivative. It simply states that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of this over h. So that is the limit definition of the derivative, and let's just put that in a little box here. So I want to use this to evaluate f of x equals x squared, like I said. So this is an extremely simple function. There's really nothing magical about it. It's an easy function to work with. It's an easy function to graph. It's always positive. It decreases from negative infinity until 0, and it increases from 0 all the way to positive infinity. It's a beautiful polynomial. It's continuous. There's no pinch points. There's no discontinuities. It's a very nice polynomial. It's always positive, so except of course for 0. So let's talk about it really quickly. Let's go ahead and start plugging it into the limit definition of the derivative. So we can recall that when we're talking about f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. The f of x plus h part means we're just going to put an x plus h everywhere we see an x, and the f of x part means we're just going to rewrite our original function. So this means that we're going to start out by saying the limit as h approaches 0 of, well, we're just going to have h on the bottom, right, of course, and then here we're going to have x plus h squared because it's x squared, right there, and then we're just going to have that minus x squared. So that's our first step, and let's just keep evaluating. Well, let's break this down a little bit. We're going to have the limits, and once you get everything plugged into this, it's really just algebraic at that point. So we're going to need to factor this out. If we remember x plus h squared, we can't just jump to conclusions and say, that's x squared plus h squared. A plus b squared is not equal to a squared plus b squared. So we're going to have to factor it out, and what we're going to end up getting is x squared plus 2hx plus h squared minus x squared. Of course, we're just continuing to bring that down, and all of this over h, or our delta x. Now let's keep working here. We're going to have the limit as h approaches 0 of, and well, let's break this down a little bit. We've got x squared plus 2hx plus h squared minus x squared, all of this over h. Well, can we not just turn this into 2 times hx plus h squared? Yeah, I think we can. And here's why. We've got an x squared here, and we have an x squared here, we have a negative x squared here. Well, it just cancels out, doesn't it? So now we're just left with this portion. So we have 2hx plus h squared. So we're just going to continue and write that on down here. We've got 2hx plus h squared, all of this just over h. And we're going to need a new page here. We have the limit as h approaches 0, and we have to, of course, remember, we have to write this limit as h approaches 0 every time, even though it may seem, man, come on, we know this is what we're doing. Well, we have to write it every time because, think about it this way. is this equal to this? Yes. But is this equal to this? No, it is not. Because this is just a function. This is the limit of that function. So the limit of this function is equal to the limit of this function. So we can't just go writing it without the limit, because we're evaluating the limit of each of these functions, each of these rationals, every single time as h approaches 0. So it's extremely important, paramount, that we write the limit as h approaches 0 of our function every single last time. So now, what were we coming from? We were coming from the limit as h approaches 0 of 2hx plus h squared over h. Well, that's just going to be the limit as h approaches 0 of 2x plus h, right? Well, here's why. Because look at it this way. We've got this h here, so we just get rid of these h's, and we're letting h go to 0, so we're going to end up having just the limit as h approaches 0 of 2x plus h. And well, this is just going to, now we can actually evaluate this limit, letting h go to 0. H is going to 0, but it's never 0, so we're just going to end up with 2x. So f prime of x is equal to 2x. That's all we need to worry about here. So we're done. X squared, when we take its derivative, is just 2x. Now, we'll find out much easier ways to do this in the future, and I'll make a video, or should at least, about how to evaluate the derivative of x squared without using limit definition of the derivative, because this wasn't a ton of work, but there was, I mean, look, there's some relatively obvious room for error in here, and I think that's not a good thing. So this is all there is to it. It's just 2x, but there's an easier way to do this, and we'll get to that. But for now, this is how we do it via the limit definition of the derivative, to get that f prime of x squared is just 2x.